About soil health. I'm going to give you sort of my perspective and ideas about what soil health is, and well, drawn broadly from the literature out there, but hopefully give you a somewhat different take. And then I want to go deeply into one potential driver of soil health that I think is really important we should be paying attention to, mainly soil macrofauna. So we're talking about earthworms and ants and beetles and all that kind of fun stuff that we love to play with in the garden. So I guess just to start, and luckily, what is soil health? My definition agrees pretty well with Jim, so we're in luck there because there's going to have issues if not. So this is actually pulled right off the NRCS website. Broadly, with the continued capacity of soil to function as a vital living ecosystem, sustaining plants, animals, and humans, right? So this is going beyond just agricultural systems, but looking at natural systems, forests and everything. Soils very broadly have a bunch of different roles. And again, I think soil health, soil quality are terms that maybe soil health has a more biological feel to it, but I think they're used kind of interchangeably in case there's confusion there. And then as Jim pointed out, often we're talking about different components of the soil. We're talking about physical, chemical, biological properties that regulate a whole range of different functions in the soil, right? So when we talk about these soil functions, again, this is right off the NRCS website. We can be talking about sustaining biological diversity, activity. Productivity is what's probably most relevant for everyone here in this room, obviously. If our soils aren't productive, then they're not doing their job. But also, they're really important for regulating water flow, water storage, filtering, buffering, degrading organic materials, right? If our soils didn't help us break down organic matter, we would just have our crop residues be stacking up in the field every year, and we wouldn't be able to grow eventually. Of course, they're really important for nutrient cycling, carbon cycling, and then just providing stability and support for plants, but in other systems, it's for support for our houses, right? So there's a lot of different ways we can think about soils and their uses. So I like to think of all these soil functions as ecosystem services, right? They're all sort of key aspects, key functions or services that soils are providing us. And I like to think specifically about a special group of these soil-based ecosystem services that I touch a lot in my work. And I kind of group them into four main areas. So first I talk about these water services. We've been talking about the importance of infiltration today, and that relates very strongly to the capacity of soil to infiltrate water so that we're not getting runoff and not getting erosion. It's also allowing for greater water storage, and then that water that percolates down gets purified, gets into our groundwater that way, and so the soils play a lot of very important roles in regulating the flow and storage and purification of that water. Obviously, soils are really important for nutrient dynamics, right? They are capturing maybe our fertilizers we're applying to the soil. They're holding on to them until a time when the plant needs them and can take them back up. But it's also regulating the recycling of organic nutrients in the soil. And so soils are very important for overall plant nutrient provision or crop nutrient provision. I know we're not supposed to say the word climate maybe, but no. They're also very important for climate regulation, right? So here I'm talking about greenhouse gases. Soils, as many of you may know, hold twice as much carbon as in the atmosphere and 3 times as much carbon as is in all living beings on our planet, right? So there is a very large pool of carbon in the soil, and it's really important that we are monitoring and trying to control the flow of that carbon, either being released to the atmosphere or vice versa if we're trying to sequester carbon. And soils are also very important for controlling the release of other important greenhouse gases like nitrous oxide and methane. Nitrous oxide being about 300 times more potent than carbon dioxide in terms of global warming. So something we need to be careful of. And these are all processes that are fundamentally regulated by soils. And then finally, soils are really important for biodiversity conservation. They provide habitat and structure for a whole range of beneficial soil biota. I'm going to talk a lot about earthworms here in a minute, but also We talk about nitrogen-fixing bacteria, mycorrhizae, and a whole slew of other microbes and other critters in the soil that are basically fundamental to controlling a whole range of processes in the soils that ultimately allow those soils to be productive. Just as a side note, when we talk about these ecosystem services, I'm talking very broadly about water services, nutrient provision services, and when we're talking about soil health, we want to link those two things together. In this column, there's sort of a list of different potential services, but each of those services may have multiple overlapping soil health indicators that we might consider, right? So, soil organic matter, for example, as Jim showed, is part of the biological component, but it's also playing a very important role. Here it's listed as a chemical component of soils, and it's also playing a really important role in water cycling and structure. So it's one indicator that's overlapping and really playing a role in a lot of different ecosystem services. Okay, so that's my introduction into sort of what I'm talking about when I'm talking about soil health. I'm talking about the ability of soils to support a whole range of ecosystem services that are important to us and to productivity in our agricultural systems. So now I'm going to switch gears a little bit and really talk about soil macrofauna as I see them as drivers of ecosystem services in a majority of agricultural systems around the world. So let's see if I do a job of convincing you here. So these things are, even if we can see them, right, these are basically things you can see with the naked eye, greater than 2 millimeters, all the crawly things you don't need a microscope to look at, right? So we're talking about millipedes and ants and earthworms and centipedes. They can be typically in very high abundance in soils. We're talking on the order of hundreds to thousands in just a meter squared of soil, so like this. They're broadly distributed. They're basically all over the world. Believe it or not, a lot of farmers, places I go aren't convinced that they're there, and we start digging around, and sure enough, we find them. They can be very valuable indicators. They're very sensitive to management, and they represent a lot of different functions in the soil, and I'll get back to that a little later. And these functions, really, they are detritivores. So that means that they're eating detritus, they're eating the organic matter in the soil and helping turn those nutrients and carbon back into a useful form that plants can take advantage of. Not all of them are good, right? So some of them are herbivores, perhaps feeding on our crops. If they're feeding on the roots particularly, we're talking about soil organisms. But at the same time, there's predators that might be feeding on these other two. And those predators, we might be thinking of as biocontrol agents that are helping regulate pests or below-ground pests. And then one of the ones I'm most interested in are these ecosystem engineers. So here we're talking about earthworms, ants, and termites, principally. And these are organisms that have very significant effects on the structure of soils. They completely re-engineer the soils by forming burrows, by forming aggregates, by moving carbon around, and they completely change their environment for themselves as well as for other organisms and things living in the soil. So, talking about just how broadly distributed they are, this is a cool map that just came out in this new Global Soil Biodiversity Atlas, which is available free online if anyone's interested. And this is the diversity of soil macrofauna around the world. So what we'll notice is that in these sort of humid tropical areas, we tend to have higher diversity. This is the red areas have generally more diversity. And generally more abundance, because there are a lot of ants and termites in the tropics. And ants and termites are really important in the tropics, but we're not in the tropics. We're in more temperate areas, right? And here, even though there's more diversity and abundance in the tropics, what we tend to have in these temperate areas are things like earthworms, which are really big, and so it doesn't take very many of them to be very important. So even though abundance and diversity might be more important in the tropics, if we look at overall biomass of these soil macrofauna and their influence, they're probably just important, if not more important, in many of these temperate areas. So with that in mind, I'm going to talk more about earthworms today. I think that's more relevant for systems around here, and honestly, a lot more research has been done on earthworms because they are so important. So I'm going to go back and forth about ants and other organisms a bit today, but I'm going to mainly focus on earthworms. So I'm going to start by looking at, this is an experiment that I conducted when I used to work in Colombia. I'm going to jump to the tropics for a minute. This is a pot experiment. I know, it's not that exciting, but it will be in a minute, I promise. So this is an experiment where in these highly weathered, acid, tropical soils. Some of the most limiting nutrients are things like phosphorus. You know, when you get really low in the pH range, phosphorus gets bound up by iron and aluminum oxides, and it's very problematic. So some of the most important inputs they apply in these systems are, of course, phosphorus and lime to try to raise the pH. At the same time, a lot of these soils are very intensively tilled, and in doing that, they're destroying earthworm populations. So I wanted to get an idea of the relative impact of earthworms versus these different fertilizer or fertility amendments that they're adding. And so I added them in all different possible combinations, you know, with and without earthworms, with and without phosphorus, and with and without lime. And what I found over the course of all these different pots is basically, okay, when I added phosphorus, I got about a 35% increase in overall biomass production. Interestingly, there was no effect of lime in these soils, which there should be. But earthworms yielded about an 86% increase, so almost a doubling in total biomass. Okay, so I know you're thinking now, yeah, right, this is some pots in like Colombian acid soils, like what the hell does it have to do with our soil here, right? So to help try to convince you this a little more, this is pulling from some colleagues' research where they conducted a meta-analysis. So they basically went in and searched all of the literature all around the world, everyone that's done a study with earthworms and plant production, right? And they found 106 studies where people looked at grasses, 154 studies looking at grain crops, and 42 studies looking at legumes. And what they found is that this is sort of the earthworm effect on overall productivity or production. So they found for grasses and grain crops that earthworms were, on average, across all of these studies, yielding about a 25% increase in productivity. So that means that some studies the effect may have been negative, but in other studies the effect may have been, you know, quadrupling of biomass. And so the average over these hundreds of studies is suggesting that earthworms are actually increasing productivity by about 25%. Now we ask, like, why is it not happening with legumes, or it's not as severe? A lot of what they think is happening has to do with nitrogen. They think that earthworms are really important for basically chewing up that organic matter in the soil or old plant residues and really quickly cycling that nitrogen back and making it an available form to plants. So they found, and so that way when we have legumes in the soil, maybe the earthworms aren't as important, or legumes have their own source of nitrogen, so that release of nitrogen is not as important. And so they found indeed that soils that are receiving greater than about 30 pounds, so this is kilograms per hectare, but it's about the same as pounds per acre. So that soils where they've received greater than 30 pounds per acre, the earthworm effect wasn't as great. I mean, it's still on the positive side for sure, but it's not significant. Whereas soils receiving lower amounts of inputs, they become a lot more important. So I think we can broadly state, like, around the globe, earthworms can be pretty important for boosting productivity. Hopefully I've got you that far, at least, in agreeing with me. Okay, so back to that pot study again. I'm going to go back to that a few times because it nicely illustrates a lot of the different concepts I want to talk about. So these earthworms and other soil macrofauna can also be really important for changing the structure of soils. So of course we know they make big burrows or big macropores in the soil, which, you know, provide a place for roots to grow and provide, you know, quick channels for water to go down to infiltrate. But the aggregates that they form, these are basically the casts that come out the other end of an earthworm, are these very stable aggregates and very highly enriched in organic matter. So this is an earthworm aggregate versus an aggregate formed maybe by bacteria or plant roots. And these tend to be much more stable. And there just tends to be a lot more of them when you have earthworms. So this is pots grown with or without earthworms, and I combined them with different types of plants. And in all of these cases, when you add earthworms, you get an overall increase in aggregate stability or the overall aggregation of the soils, except when you have no plants. And what this is saying is that you need to feed the earthworms. You need to give them some sort of food or organic matter, which in this case may be plant residues or roots, or else they don't have that glue basically after their casts come out to hold those casts together. So yes, earthworms do these amazing things, but you need to feed them in order to see a lot of these effects. So overall, we see about a 32% increase in this aggregate stability, or this mean weight diameter is a term we use. It's sort of the average aggregate size. And you may be saying again, well, yeah, so what does that mean though, right? So soil structure and these aggregate stability is really important for, like I mentioned, things like infiltration. The more larger aggregates you have in the soil, the more larger pores you have between those aggregates that water can flow down through. The air can come down through, and for general aeration in soils. So this is a student I worked with up at Ardec near Fort Collins, and he found that as you get more individuals of macrofauna, here this is largely dominated by earthworms, you tend to have higher infiltration rates. And it's a pretty nice correlation here, I mean, across his fairly small field site, with not that big a treatment differences, that generally these more earthworms is definitely getting more water into the soil faster and reducing the overall risk of erosion and increasing overall chance that water gets captured for later use. This is an irrigated corn plot, but I mean the same concept goes in dryland. And this is just an example, basically looking down on these infiltrometer rings, the same Cornell infiltrometer that we talked about earlier, that, I don't know if you can see that from here, but this is one that had a lot of macrofauna, and you just see there's all these little dots, giant pores and aggregates, and there's very textured soil. It kind of looks like, I don't know, Swiss cheese almost, or fresh cheese or something. It's very crumbly. Whereas this is one with very low macrofauna, very low infiltration rate, where you just see there's this block of soil, and there's not a lot happening then. There's not a lot of obvious pores. So earthworms are also very important for water movement, potentially in soils. This is another cool example, back to the same plot study in Colombia, where I said that lime by itself had no effect on overall plant growth, but that wasn't totally true. I wasn't considering interactions there. So here is a pot, the control pot, and here we're growing beans, and here's when you add lime. Nothing happens, right? Then you add earthworms by themselves, you get a little bit of bump in productivity. But then when you add lime and earthworms together, the earthworms are somehow, I don't really know the mechanism here, but they're somehow activating that lime and really making it have an effect so that this plant can either uptake or fix a lot more nitrogen. So in that sense, earthworms can enhance the efficacy of nutrient amendments that we are adding to the soil. I'm just going to grab some water. Okay, and related to that, this is another study I did where I applied fertilizer, nitrogen fertilizer, to the soil, and it was labeled with a stable isotope of nitrogen, 15N. So you're able to trace where that nitrogen goes into the soil and into the plant and figure out how much of it you lost, how much of it stayed in the ground, where it went. And what we found is, most of what I've been talking about is the effect of earthworms on organic forms of nutrients, on the things that were bound up in plant residues and in other parts of organic matter in soils. But here what we found is we added this 15N labeled nitrogen fertilizer to the soil, and earthworms resulted in a significantly higher portion, it's about a 7% increase, of that fertilizer ended up in the plant when earthworms were present. It's interesting because the plant didn't really grow much more in this case, but somehow they were able to channel more of that fertilizer into the plant, which has, it's only a 7% increase, but when you think about this occurring over a large, many acres or a large area, that can be pretty important in terms of, ideally we want to get more fertilizer into our crops. So if we can get, organisms that help facilitate that in the soil, that's potentially a beneficial thing. I more emphasize it here, not for the huge effect, but just that it's kind of interesting. We don't really have an explanation for that either. Okay, so hopefully at this point, earthworms are increasing plant productivity, hopefully the efficacy of our nutrient amendments that we're applying, as well as improving the overall structure of soils, improving water dynamics and a whole other range of things that go along with that improved structure. So hopefully at this point you're convinced that they're beneficial and they're something we want, and I probably didn't even need to go through all that to convince you of that, but that's just how I work. So the next question is, well, how might we go about managing these macrofauna communities in general to better regulate the services that they're essentially controlling or influencing a lot? So I'm going to start with, this is experiment out in the Central Valley of California. So again, we're on irrigated land here, but they basically have these systems. This is a no-till with cover crop. This is tillage with cover crop, no-till, no cover crop, and then tillage cover crop. And what do we notice from this, right? That, well, no-till alone is not really doing it. And cover cropping alone is not really doing it. I mean, there's a slight bump in terms of overall macrofauna abundance activity compared to the till no cover crop. This is kind of the standard. But it's really when we get those two things together, it's the lack of disturbance you get with no-till together with the cover crop is like the food, basically. So stop chopping it up and feed them, and all of a sudden, you know, you get a lot of earthworms and other types of macrofauna in these soils. And you get all, you know, those benefits that come along with that to soil structure, you know, you start getting realized after a couple of years. Also, we look at overall diversity of the organisms we find in the soil. Again, when you have no-till with a cover crop, you tend to get a lot more types of different organisms. And, you know, at first, it's kind of like, what does that really mean to us? I think of these macrofauna as sort of integrating organisms, as they're representing a lot of the, you know, they're feeding on smaller things that are feeding on smaller things that are feeding on microbes. So, you know, the more variety and the more diversity we have of these things is an indicator that we can pretty readily look at ourselves, you know, and qualitatively say like, hey, this soil is more diverse or more biologically active than another soil. So now this is from research site in Akron. Again, this is irrigated fields, so we have to be a little bit careful in terms of how this applies here. But so in this experiment, this is corn where they're growing no-till with corn residues kept on the ground, right? And this is no-till with corn residues basically moved off, you know, packaged where the stover is removed from the field and used for feed or whatever they're using it for. And then we have a tillage with residue contained, and then tillage with no residues, which again is probably the most common state. And again, we see a very similar pattern that it's only when you leave them food, you leave them that corn stover on the ground, and you stop tilling that you start getting these you know, huge amounts of earthworms and all the benefits that go along with that. And here we actually went and wanted to quantify some of those benefits. So first we looked at aggregation in the soils. These are fresh graphs I made in the car on the way here this morning, so it's just like new data. And we see that indeed, more earthworms, you get more aggregation in soils. You know, it's quite a bit more. It's about double what you see in these other soils. And we went beyond that. We looked not just at aggregation, but we looked at, well, how does it relate to water infiltration? And this data still needs some cleaning up a little bit. It's a bit noisy, but we still see that there's this general trend that you're getting much higher infiltration in the soil that's better aggregated due to all of the earthworms. So in this case, you know, for me, it's pretty nice evidence that managing the soil in a way that's encouraging these diverse groups of macrofauna is leading to much better functioning of that soil in terms of water capture and erosion control. Okay, another example, so we're going to jump down to Brazil now just very quickly, just to illustrate a point, is that it's not just about how you treat the soil, but it's about what you grow there. So here this is pastures basically grown with, this is called a forage peanut. It's very common in the tropics. And basically when this forage peanut, this leguminous, you know, high quality plant was there, you had about twice as many earthworms on average as opposed to pastures that didn't have that. Now I'm going to jump away from earthworms because in the tropics they're not all important. You know, just the same way, this is a very common planted pasture grass, improved pasture that's planted throughout the tropics. And when there's pasture there, you tend to have a lot less ants, right? So it's just trying to emphasize that the different types of plants that we have in a pasture and our crops are all going to influence, you know, the resource quality and availability of food for different organisms that are living in the soil. Okay, so I'm jumping all around the world here just to kind of illustrate that these concepts don't just apply to Colorado, but they're concepts that we can take in all different systems, and you know the same general things are applying. So now we're in Nicaragua. And here we're looking at overall macrofauna abundance in secondary forest. We're looking at traditional slash and burn agriculture or pasture, or agroforestry system, where they're no longer burning, and they're basically applying all this mulch residue. They're pruning back trees every year and applying all this mulch residue to the soil every year, which essentially protects the soil from erosion and acts as a food source for all of these critters. And because of that, you get a significantly higher number of critters, and earthworms included. This is the earthworm casts on the soil surface there, so a lot of them are earthworms. And again, so this is a reduced disturbance and provide food, and you get more of these organisms coming, right? It's kind of a field of dreams in a way. This is another experiment in El Salvador where we're trying to restore degraded lands there. So this is land that's been under slash and burn agriculture on really steep hillsides for many years. And we tried some agroforestry technologies as well as organic agriculture. We were applying compost. And we found that both of these, agroforestry and compost, significantly increase the overall earthworm abundance, at least on these soils, which is going to help, again, with getting more, that's really important here in terms of reducing runoff and getting more water stored in the soil for subsequent crop use. Because these are dry land. They are very wet, but they are dry land systems that are, or rain-fed systems that are completely dependent on precipitation. And this is just the traditional system here that you see is much lower, as well as the secondary forest. So again, that's all sort of about disturbance and organic matter management. But here's another example from Northern California near Davis, where I used to be based. And this is a farm run by a very influential farmer in Northern California, the Rominger family. And they came to us with a study and wanted to understand how they could change their overall farmscape, we're calling it, to better support biodiversity and ecosystem services. So these are two big tomato production fields. I think they're about 40 acres each, or maybe the top one's about 40. I don't remember the numbers exactly. And we looked at a bunch of different components within this farmscape, elements that are making up this farm. So we looked at the tomato field, of course. This whole bottom area is a riparian corridor. There's a small creek that runs through there. So we want to know how that's contributing to all of these services across the farm. Hedgerows are a really big thing now being promoted in a lot of Northern California especially, due to sort of issues with honeybees and pollinators and all of the orchards around there, almond orchards in particular, right? So a lot of plants requiring pollination, and so they're trying to enhance native pollinators by promoting hedgerows among farmers, and they get subsidies to plant these things, and most of them are native. They also have a tailwater pond. This is all furrow irrigated, so this is an effort to catch any runoff nutrients that come off, as Jim was talking about with our furrow irrigation, and then they redistribute that on the field every few years. And then drainage ditches are a pretty prominent part of this farm, and we just want to understand what they're contributing as well. So this is, again, looking more broadly at a whole range of different ecosystem services. And of course, if we're interested in carbon storage, these forests do a pretty good job. There's a lot of carbon locked up in those trees. But even planting those hedgerows is significantly better than, these other uses, the tomato field or the drainage ditches, right, in terms of carbon storage, because all of that carbon is basically in the soil. If we look at nitrous oxide emissions, this is probably one of the more important greenhouse gases, at least with relevance to agriculture. We see that, again, these hedgerow and riparian corridor are the lowest, where these drainage ditches, where you have these very anaerobic conditions and runoff coming from the fields, is where you tend to get the most nitrous oxide emissions. But I want to talk about how we want to support overall soil biodiversity. So within this, we looked at vegetative cover and diversity. These are all different types of plant groups. We looked at earthworms, and we also looked at microbial communities using this phospholipid fatty acid analysis that Abdel talked to us earlier about. And what we find in all of these is that, again, having these perennial components on your farm, or on this farm anyway, helps support biodiversity across all of these different organisms, really. And, particularly for earthworms, it may be very important if you are tilling your field to have a source for recolonizing your field, in times when if you're going to stop tilling for a while, that you have source populations to sort of recolonize and get these beneficial organisms. The flip side of that is maybe it's a source population for weeds and things like that we don't want as well. So you kind of have to balance those things out a little bit. Anyway, using these examples, we kind of went through an exercise together with this farmer and said, like, what are your options? And so here's a schematic or a layout of his farm. And we said, like, okay, you could cut down all of your hedgerows and the riparian forest that the state allows, and you could just plant tomatoes everywhere, right? And we said if you do that, you would bump up your production by about 5%, just based on area. But at the same time, you would be losing zones where you have high infiltration, you'd be losing carbon storage, and you'd be losing diversity of all these different organisms here. Earthworms is a bad example here because it's earthworm diversity and not abundance. If we had put abundance there, it would have dropped off tremendously, but unfortunately I found every single one of the species of earthworms in all of the land uses because they are fairly mobile. There were just a lot less in the fields and whatnot. So with that caveat, I'll continue. Okay, so the other option was, okay, well, starting from that full production mode, what happens if we go back and maximize the number of hedgerows around this farm? Like, what's that going to do for overall, or all these different services? So here you see now all of the field borders have been planted with hedgerows. And now we get back a significant amount of a lot of the plant and other sort of below ground diversity. We get more carbon storage, a little lower in terms of nitrate leaching. So these are all good things, right? And we can max it out and get, this is now the max perennial option. We bring back all the riparian forest and the hedgerows, and this is sort of the maximum that this producer would consider, and including perennials on his farm. And there we get, even more carbon storage, better overall control of water, and of course our diversity can't go up because that's sort of a biased indicator there, because we can't project beyond the amount of diversity we already have on the farm. But anyway, we could at least get it up to the maximum that is currently observed. So I think that's clear, but I guess we can come back to those questions. Okay, lastly, I just want to talk about, I mentioned that these macrofauna are important indicators of soil quality and health, and we can use them as sort of a quantitative and qualitative assessment to understand how our soils are doing. So going back to this experiment in Nicaragua, we had this question of, well, can we relate these different macrofauna groups? There's a whole lot of different things we're finding to specific soil properties that are relevant to land managers or to ecosystem services. And so we went through this process where we first went through and measured a whole range of different soil health, soil quality indicators, soil organic matter, available phosphorus, texture. And then we came up with these, as Jim pointed out, it was a slightly different method. We came up with these indicators that kind of group variables together to come up with overall indicators for soil physical health, soil chemical and biological, quality in general. And then we found different groups of soil macrofauna that statistically related to those different indicators. So we were able to say, like, oh yeah, when you see that ant, that is related to having a high physical quality of the soil, or something like that, right? And then once we came up with about a list of about 30 organisms that were statistically associated with particular soil properties, we went back to the farmers in this community and basically said, like, okay, we brought them a sample of all these insects and said, which ones do you recognize? And they went through and picked out about 10 of them, and we asked, well, okay, what would you associate this particular beetle with? And they'd say, oh yeah, when I see that beetle, I know my crops aren't gonna, grow very well, and there's something wrong with it or whatever. And so if our indicator said that, oh yeah, that beetle's significant for poor chemical fertility, then we would say, like, okay, that pretty much is in agreement with what the farmers are saying. So we basically had the farmers validate our indicators, and we were able to come up with about 7 validated indicators that both our scientific methods and sort of the farmers came together saying that, like, yeah, these would be useful in terms of macrofauna that we recognize and say something about the soil. So for example, when we came across this millipede or this spider, those were present only when you had a lot of different organisms and a lot of biological activity in the soil. So when you found these, you tended to find a lot of other life crawling around in that soil, right? When you found this ant, this is a common leaf cutter ant actually, there it is right there. That was actually an indicator of poor physical quality, so compacted soils generally. And it's kind of interesting because this ant is also a pest. It eats crops and feeds on them and brings them into their soil. And, you know, rather than saying that it's a pest, maybe it's an indicator that the soil is having problems and it's more of a symptom than a problem they should be thinking about. And that they should probably plant a cover crop or let that land rest for a little while and recuperate. Again, this spider was only found and farmers noted when soils that were just plants weren't growing very well, and we indicated that had soil poor nutrient availability. So that might be an indicator of when you find that spider, you should probably add a little extra fertilizer. Right? So I know that this applies a lot more perhaps for farmers that don't have access to soil tests, you know, living in, you know, rural Nicaragua, but I still think that there's applications around here. You know, it's not that hard to go take a shovel and dig around your field quickly and see what you find and get an idea, at least quickly, of, you know, should you be worried about things or not. I think there's potentially some tools here. So just to summarize that, these macrofauna are really good indicators because they're very sensitive to change. You know, like as I showed earlier, like earthworms don't handle tillage very well, but none of these handle big changes like tillage or burning or they're sensitive also good things like adding organic matter, right? So they're very rapid in terms of responding to these new changes. They're sensitive. They're easily identifiable. You don't need any special techniques in terms of, you don't need a microscope or anything. You might need a magnifying glass depending on your vision. And, you know, they often indicate, particularly in the case of earthworms, they're indicating, or they're affecting the same soil properties that they indicate. So if we see earthworms, you know, they're indicating that there's good drainage or there's good you know, aggregation, things like that. And that's because they're directly affecting those things. So that makes sense. Okay, so with that, I just want to conclude some sort of points to drive home today. That these macrofauna, again, my very biased and personal perspective on soil health here, but hopefully it gives you something here today, are really important drivers of a whole range of different ecosystem services and soil processes that we really should be considering when we're talking about agro-ecosystem management and managing soil health. Again, if we want these macrofauna, earthworms in particular, we need to be feeding them, whether that's residues or manure or cover crops. And we need to avoid disturbing them, right? So that's potentially tillage or burning or pesticides. And, you know, they tolerate some, but it's just being recognizing that we need to do those things. There's also opportunities that greater plant diversity or overall farmscape complexity can help support these communities and the services they regulate. And again, I just mentioned that these organisms are associated with a whole range of different properties and ecosystem services, and because of that, they're very valuable indicators of soil health. So with that, I'll leave it if there's questions, or what I'm doing on time here. Okay. Yeah.
It's the guy who knows survey, Jim.
Yeah.
Didn't you comment that with no-till, that it's sealed with soil as it works? So where do you find the balance of maintaining the microfauna by if the no-till, or is it one seals the soil? You know, I mean, I understand, but you know, it's kind of a mixed bag here where we've got to find the balance of no-till.
I would say if you're able to maintain some sort of cover, mulch or living cover, then you're probably not going to get that sealing to the same extent. And I've seen many no-till soils where farmers indeed have told me that they're not sure if there's earthworms there, there's probably not, and I start digging around and you see that the soil is covered with cast and there's very obvious pores going down into it. So I think part of it is maintaining that soil cover. Like, as I showed before, if you didn't have both no-till and some sort of food, be it a cover crop or residue return, then you weren't getting the earthworms there in the first place. So I think there certainly are situations where you do get that crust with no-till, and maybe it does need to be managed through other sorts of intervention, be it cattle or, I don't know. I think plant covers is a big thing though.
So that's probably not a really stupid question, but let's say you don't have, I mean, if we've dug and we're not finding earthworms, let's say you really don't have earthworms. Where do they come from? Do we have to bring them in, or do they just appear?
So they're around, right? I mean, all of the earthworms we have in our soils, I doubt anyone in this room has ever seen a native earthworm. They're all imported from Europe or Asia pretty much. And so they've made it all around the world. But if you're farming very large expanse and have been tilling heavily for a long time, it may take a while, right? So you may find places where there are more and bring them around. They reproduce, a lot of them, pretty quickly. I've seen figures of like 5 meters a year in terms of colonization, which is slow or fast depending on your perspective there. So 15 feet moving in every year. I think they go faster, but yeah.
Yeah, I'd like to add to that a little bit. They'll migrate. So they'll migrate from more habitable areas into areas that become more habitable over time. So they'll migrate from the forest and things like that. It takes time.
Yeah, we did a study, we did a big study of earthworms in grasslands, and we couldn't find any. And they were all in all the ag fields. So we go to grassland, dig a hole, we couldn't find earthworms, go to an ag field right across the street. Love with earthworms. So they're all introduced, about 95% of species.
And I think they're in the grass fields as well. I don't know, they haven't been looked at that well in dryland systems that I can tell, but where I've been poking around so far, in the short time I've been in Colorado, I've had a number of producers tell me, no, there's no earthworms there.
You can find them.
And you start digging, and there's very clear evidence that they're there.
They're introduced.
Yeah, no, for sure. Just to point out the methodology that I think was used to go after the earthworms here before, you guys used the mustard?
We did that this past spring, and then I went out this past fall and just did a hand separation and dug up like a cubic foot. But it was really dry when I went.
Yeah, so
We don't really do it this spring.
they go down, they migrate down, and the mustard technique only works for like a very narrow ecological category of earthworms, so that's not what you want to do.
So I might find more.
Steve, did you do, I might have missed it, did you do phosphorus on the earthworms too, to see what they did to phosphorus chemistry at all? I mean, you pointed out nitrogen. Did you look at phosphorus?
Yeah, they did increase the phosphorus uptake in those plants as well. I just was trying to blow through it faster, and there's kind of conflicting evidence, like that it's thought that they increase the phosphorus availability in their cast, but by creating these big macropores, they may actually be causing it to drain out faster in the soil, so it's not super straightforward. Yeah, but I can't believe how many places I've been where people are telling me like, no, there's no earthworms there. From high Andes in Bolivia, I had professors telling me like, you're not going to find anything up there, and I find them. So it's a matter, they're not everywhere, but they're pretty common, and they can be there if the conditions are right. But like I'm saying, if you're not managing your cover and you're tilling a lot, you're not going to see them, and it's going to be a while before they come back. So.
But it's not like they're just sitting in the ground waiting for conditions to be right. They have to come from somewhere. If they're not there now.
If you till some, often they'll burn down in the soil when it gets dry, right? And then if you time it right, you can till and it'll be okay. But if you've been doing intensive tilling for a long time, yeah, they probably aren't there. So.
Well, I have a question for Jim. The crusted, is that mostly due to soil type or to mountain?
It's a kind of a combination. It's really, so the question was the crusting that I've observed. I don't know. Part of it's due to soil type and irrigation. Okay, so you irrigate lightly. Well, theoretically, you irrigate lightly in the spring to get something to come up, and then it dries out and it just crusts over. The other issue you have with no-till and those systems is that sooner or later the implement just bounces across the surface and never goes in. It takes like 3-4 years, but then you can't drag a no-till drill through that system. So it's sort of, you can get by with a minimum till, or what do they call it, where you just till it. Strip till. Yeah, strip till. We have a strip till. Well, where I used to work at a strip till unit. That'll get by. And that's probably more the way people should probably be going. But yeah, the crusting it's a combination of the soil and the irrigation and timing.
Right, because there's a number of dryland farmers have been going no-till for 20, 30 years, and they're doing fine, right? So
have they did studies like in Eastern Colorado, anywhere in Colorado, especially in Dryland, looking at macro, fauna, earthworms, dependence of earthworms, and what facts, and like you said, they need food. but like, like no-till, there's a lot of no-till in Eastern Colorado.
Yeah.
Pesticides, surely they affect how many earthworms, but how much affect to herbicides or pesticides in general have on earthworms?
I think that depends a lot. I mean, obviously they're very sensitive because they're soft tissue and stuff, but I've done a little experiment just with like glyphosate and didn't really seem to have much of an impact. So yeah, I don't know that there's a ton known about that. But in terms of what's been done in eastern Colorado, I mean, Gene mentioned the study you guys did, but was that an irrigated land where you found them all, or was that dry land?
What's that?
The study you mentioned, it was dry land, okay. Yeah, because I haven't found a lot of literature looking at macrofauna in eastern Colorado and dryland ag. I've seen a bit in irrigated, but not a whole lot in dryland. And often, most of it, earthworms are the most important in a lot of North America, but most of the studies that have been done have only considered earthworms and are ignoring all the other potentially important organisms that are there.
So if there is, I know, like when we're looking for earthworms the first time, and we did it on the lawn, just test the method, and then when there's water, they come up on the surface. So when it's dry, how deep could they go to find moisture?
They can go pretty deep. I mean, 50 centimeters or more. I mean, so it depends though. Some of them have ways that, they go into sort of dormant stages where you might not even see them because they just curl up in little balls and shrivel up even. And so they're hard to find when it's dry. So it's really a thing of, finding them, going out the right time of year, when it's wet and when it's not too cold, basically. So.
We've experienced, dryland grasses, we've experienced something that I think is called a black beetle, or a grass beetle. I think Joe Brewer introduced this to us. Can you tell me anything about those, what they indicate, how to get rid of them, especially without damaging other systems?
No, I'm not. I mean, I'm not yet familiar with this part of the world enough to know what that would indicate, but that's, certainly something that if we were to go and look at all those macrofauna and see like what types of soil properties they're associated with, that would be the kind of approach that we took, at least in that study in Nicaragua and taken elsewhere. So they're probably feeding on the roots, but there's also a lot of organisms, a lot of beetle larvae that do feed on plant roots, but that's a symptom of soils that have low organic matter, because they'll generally feed on organic matter, but when there's not enough of it, they go attack plant roots, at least one that we commonly see in Central America. So again, it's not always clear, a lot of farmers would be like, oh yeah, this one's eating my corn, but if in a healthy soil, it's not. So.
Seems to me like the high arid Colorado Plateau has been discovered yet in terms of research.
Yeah.
I'd like to change that.
Okay. Sounds good. One more question, and then maybe I'll
back on your apron, I thought that was interesting that no-till was highly good, and then the minimum till, but then when you had your conventional tillage, there was still an increase in microfauna. What can you attribute?
Well, so it was just no-till or conventional till, and then it was with or without residues being left, right?
I don't know. I remember that it was an interesting.
Can I go back?
It's about me.
No, I'm only allowed to advance forward in this presentation. Oh, that's a recording.
Yeah, it's a recording glitch.